a very warm welcome to all of you to this very first opening session of the local chapter EAGE Stavanger. At the outset, I really want to thank EAGE and Ilyara in particular for really supporting this local chapter. And all my sincere thanks to all the founding members as well who come together last year during the pandemic, of course, when obviously we were not meeting physically. We came to know each other and we worked together to form this community last year, back in November 2021. I guess most of you are aware, but any EAGE member obviously can join this. We also welcome non-EAGE members to join any online activity or the local chapter LinkedIn community as well, or group as well. Now, when it comes to today's talk, I guess we all are very much aware of digitalization, AI, IoT, cloud compute. These are all very common terms when it comes to the energy industry. But we would all agree that lately there's a huge momentum in our industry, especially the energy industry, with a push toward low carbon footprint and other things, collaboration, openness, and whatnot. And I would say this talk, especially this session, is very much tuned to that. I'm really pleased to have three esteemed presenters here. We will start with the talk from Dr. Eric Larson, who is Chief Solution Officer, Earth Science Analytics, and he will start from digitalization in the energy industry. The talk will be around 20 to 25 minutes. We'll have follow-up questions, and then we move on to the next interesting topic from Steve Freeman, who is Head of Energy Transition, DNI Schlumberger, and he'll be talking about the role of lower carbon energy in meeting the world's growing energy demand. And then we will move to the last, but I would say not the least and the most interesting one for me, is where Egil Tjaland, who is Associate Professor NTNU, who is going to talk about evolving role of academia for the future of geosciences. With absolutely no further ado, I would hand over it to Dr. Eric Larsen. Please start sharing your screen and I'll stop.
Thank you very much, Surander. And thanks not least for the efforts of setting up this local chapter. So I'm really looking forward to being a part of it. And thanks for the opportunity to present here at the opening. So my talk, do you see the slides now? Yeah. So the title is here, Digitalization in the Energy Industry. It's very broad, but I guess in an opening talk, we can be a bit high level. So I'm not going too deep into the technical parts, but I'm sure later on in the local chapter, we'll have real deep dives into various technical issues. So I decided to put up a word in bright letters here at the top, transformation. So I think that's what we're living through now. So changes are always happening, but I think now we are seeing change at a bigger change and faster change than we have been used to. So we have this backdrop that we are living in, the energy transition. So obviously we need a reliable energy supply, and we need to make sure that this energy supply is also sustainable. In addition to the energy transition, we're living through the digital transformation. We see a lot of talks at various venues on innovation and earth science technology. I think this is what I'll focus most on in this talk, on how we're doing this digital transformation, and highlight the need for collaboration in order to scale beyond the many cool demos and POCs that we have seen, and really move towards Industry 4.0, as it is called. So just highlight a couple of problems at the start here. So obviously in the energy challenges, we have climate change, CO2 emissions as the backdrop. We're also seeing, I think in the last 5-6 months, we've seen the effects of undersupply of electricity, gas, especially here in Norway on the electricity prices, and in Europe on gas prices. And there is some sense of urgency to solve these CO2 emission problems and climate change problems. So the rate of transformation to zero emission economy is basically going too slow. So we need to then, of course, work more on renewables and make sure we have a zero emission energy supply. And CO2 storage that we will get into will be a part of it, as long as since we do expect that we will continue with hydrocarbons for a long time still. There are also challenges on the data side. I think I've seen at least 100 talks about data being inside silos and not available to those who need to use it to do analysis and support decisions. Another topic that frequently comes up is the quality of the data. It's too poor to just push it into some machine learning model and expect it to work well. We're also seeing like the kind of lack of domain expertise. A lot of people are retiring, and there are a lot of other jobs outside the petroleum industry that are competing for talent these days. And I think at this moment, the last couple of years, we've seen a bunch of POCs, but we have seen too little of innovation that makes its way into production and is really used to make an impact on decision making and on solving these problems, both on the energy transition and the digital transformation. So I think one key part of the data problem is that we have these huge data sets that could have been used to really do great things, but they are still severely underutilized. And the solutions we'll look into is, of course, the open data ecosystem, which is a core element to fuel innovation, collaboration, the innovative applications itself, and the use of data science to transform the earth sciences. That's just an illustration found online that we're seeing that there's a lot of efforts in the early stages of this data analytics marathon, POCs, things like this. But rarely do we see that the projects are completed and taken all the way to the value creation. I think that's something we should be focusing on increasingly from now on. But this is obviously not an easy task. And in my company, Earth Science Analytics, we started off focusing on the machine learning side of things. So the ML ops in the middle here. But then we quickly realized that we need a lot of tooling and infrastructure to deal with the data. So we have to do also the data ops, the data platform, and make sure that the data flows smoothly through all these applications. And only when you have the two can you move on to real intelligent automation of the earth science solutions. We see on single use cases a lot of proven value. Many things we can do now with AI-fueled technology, 10 times faster. We can be more efficient. We can save costs. We can identify new opportunities at a large scale. So the value is there to be had if we just manage now in the next months and years to scale it properly. So back to the energy problem. So the world needs the sustainable and reliable energy supply. Can we as geoscientists and as geoscience technology developers help solve this problem with the next generation earth science technology? And I firmly believe so. And CO2 storage is a key part of the solution, which means we need to find, characterize, and monitor a bunch of storage sites. So in that endeavor, we need our geoscience knowledge, and we'll also need to find new ways of working to do this, because it needs to be done faster than we could with traditional methods. And it also needs to be done cheaper, because cost is an important factor here. We have here in Stavanger a very cool startup. It's getting quite big, that is transforming stranded gas in the Barents Sea into sustainable energy, basically by producing hydrogen and ammonia from this and re-injecting CO2 into the subsurface. So I think that's a really cool example that they're doing in Horisont Energi to make a business out of this energy transition. So I really hope we see a lot of use cases and companies like this, and that this becomes a success. We'll see also the need to develop offshore wind. Big plans to do this at a huge scale. Of course, when you build these sites, you need to map and monitor the seabed and the subsea infrastructure. So also there is a need for earth science competence and technology. Hydrothermal is another one. We need to find and develop new sites. And a common thing to all of these is that I think that the solution is that we should be able to do this as profitable businesses, like doing CO2 storage as a business. Of course, there are costs to this that can negatively impact the profitability of such a business. So we, from the earth science side, we need to be focused on how we can do our work and keep the costs down. And I think technology development and new ways of working is a key part of that. So then back to this one of the two fundamental topics here, the data challenges. So it's this point of data being siloed. We used to have applications that each application had its own data storage system, and it was, well, it still is inconvenient to move data back and forth with FTP and all that. Lack of finding the right data to use it takes a lot of time. We heard it many times. The data quality, we're suffering from this. It takes a long time to clean it up. So I think the efforts, I'm sure you've all heard about OSDU and this open data platform. I think it's really key that this in some form really succeeds and becomes mainstream. So that there is an open data platform with open APIs. So all those innovative people and companies can develop applications that leverage this. That will really fuel the innovation and the ecosystem of applications that become available. And these applications, they do specific things. There can be very narrow applications like using AI to interpret faults or horizons or geobodies. It can be a machine learning to do petrophysics, to make porosity logs, saturation logs, etc. Technology to speed up and partially automate well tie, and so on. So we'll see applications that uses machine learning to do all these classical geoscience tasks and increase the efficiency in that. But there is also another level of integrating the workflows. So I've heard since I was a student that we should focus on integrating our disciplines and our data types. And now with these data platforms that are emerging, this becomes possible to do and to scale. So to the left here is just illustrated one form of this data platform. This is the one that we have in our company. It's compatible with the OSDU, and it feeds the data into all these individual workflows with different colors here. And these workflows also communicate with each other. So that if you want to have, for example, a porosity volume in 3D for your field, you would need to do the petrophysics workflow in orange here that feeds information into the 3D property prediction workflow in blue. And you can also support this exercise with information from the green seismic interpretation workflow. So it's not just one machine learning model or AI that solves this puzzle. It's a combination of many. And so although AI and machine learning is narrow at the moment, we don't see that it's general in the meaning that one AI can solve many tasks. We can build a team of many machine learning models that together can solve very complex tasks of basically mapping the property distribution of fields and prospects. On the data side, big heads up to Discos. It's been a huge success. And of course, there's a next level of Discos where the information flows more smoothly to the applications and back to the database. So that is something we did in our company. We basically digitized all the released well data and sample data from Discos. So this is now readily available to use in machine learning workflows. It's also been curated, QC'd. And so we built a lot of technology to do so efficiently. And once you have such an asset, you can do a project such as this that we did in the collaboration with the NPD. Basically to do petrophysics of 500 wells in the North Sea. But this is the machine learning version of petrophysics. But it produces lithology logs, saturation logs, porosity logs, and pay flags. And with this output information, you can identify, of course, accumulations of oil and gas. And we see that we were able to identify many such accumulations that were in wells that are officially classified as dry wells. So something like this that we also did in the UK, supported by the OGTC, now called the Net Zero Technology Center. So we've been able to do this kind of exercise on all the released wells from the Norwegian North Sea and all the wells from the northern UK North Sea. So this is an example of the scale that we can do things with now. So many thousands of wells in a matter of months to highlight overlooked opportunities. We can also see new business models. As an example with TGS, the data company. So we set up a collaboration with them, and collaboration is also a key part of this. So we use our technology to basically interpret their data. And this example is from the Ocean Bottom Node survey in Utsira High. So we provide highly detailed rock and fluid property prediction, including also the elastic properties based on this highly advanced seismic survey. With this technology that enables us to predict rock and fluid properties from the seismic, we can identify accumulations of oil and gas in 3 dimensions. This was also studies supported by the NPD and with data from CGG. And you see here the Grosbeak discovery that initially was overlooked in the first well, but people who were really digging deep into the data saw that maybe there is something here anyway. And it was proven a success with the next well. But we see that it was possible to find this smoking gun of hydrocarbon saturation in the first well with this machine learning approach. And it was possible to map this out in 3D with a 3D property prediction approach. So now this is a methodology that can be scaled and used as an exploration tool to look for overlooked opportunities, which is happening now at a larger scale. This technology. So the combination of the data platform and all these individual tools and the integration of these individual tools allows us to work on different scales. So you can work on the well scale with the well logs. You can work on the seismic scale that was on the previous example. But you can also dive all the way down into the sample scale. So there are some rock samples. It happens to be cuttings, but it could be any kind of rock samples. And with the deep learning, it's possible to interpret this data on the pixel level to say that these are shell fragments. This is a piece of sandstone and mudstone and so on. And that information from the samples can propagate into the well domain, be correlated with the well logs, and then from there propagate all the way up to the seismic scale. So now we're linking from the very small to the regional picture. And in order to scale this, we set up another collaboration with Rockwash Geodata. That is the company who actually obtains this data. They have the machinery to do so. And they also, importantly, have the competence to provide the training data that we train these machine learning models on. So now we will be doing this on all the released samples from the Norwegian continental shelf. It's at least more than 700,000. It might be even more. And in addition to that, we're also doing it on Rockwash's proprietary images, and we'll take it further with other types of images. So that's an example of how we can take a data asset that was previously dormant. It was there, but it was not frequently used, and turn it into a useful interpreted form that can then propagate this information into other larger scale workflows. These were techniques. Of course, they can also be used for subsurface carbon storage. So in this example, we have some machine learning models here that have interpreted the extent of the CO2 plume and the Sleipner injection site in over time based on the 4D data. So this one just shows the distribution, but we can also use the property prediction technology to map the distribution or the property distribution of the reservoir and the seal and of the fluids themselves. Another thing with CO2 storage is that if the storage sites are fault bounded, it's important to understand the risk of leakage through the faults. And this is an example where my company collaborated with the University of Oslo to map the likelihood of fault slippage that could result in leakage from this site here east of the Troll field. Also using machine learning models to interpret the faults in high detail with every sample in the dataset. The energy transition or the green shift will also require us to have better access to minerals. We see activities on the deep sea mining side. Of course, it's very important that this activity is also done in a sustainable way. So this is an exciting field to develop technology for, both for mapping the mineral and metal resources, doing the resource estimates, but also for mapping the ecology and the impact that might be on the environment, so that the decision makers can be informed on the possible environmental impacts and make good regulatory decisions in that field. And again, machine learning comes in as a tool that can make us more efficient and deal with large amounts of data in this space. These things aren't easy to do. So it's a long way to go from a cool demo or a proof of concept to putting it into operations. So you basically need an end-to-end tech stack. So you need the data ops, the data platform that needs to be open, and like we see the efforts with OSTU. We need data labeling software because currently the the commercially attractive part of machine learning is supervised learning that needs to train on ground truth. We need to make sure that everybody can be data scientists. So we are scientists, we work with data, we should be able to be data scientists. But not all of us are coding superstars. So we develop a codeless model training software. We need to be efficient in our ability to develop applications for each specific use case, because DevOps, making sure we can deploy this in the cloud, on-prem, on the edge efficiently. And number 6 here is MLOps. So a model can be great once you have tested it on your test set, but it's a fact that when you expose it to more data from the real world, eventually it will not perform well. So you will need to be able to detect when that happens, and you need to be able to mitigate it and provide a better version of this model. And that's why this is set up like a wheel that you'll have to go around and round again and again to make sure it works appropriately. So to summarize, I think my main point here is that digital transformation can and will support the energy transition. We can accelerate most workflows. We can achieve higher productivity, which is important to reach the net zero targets that have been set. We can save costs by doing so, which is important for being able to drive the energy transition as a business, as a profitable business. And we need to do so also in a robust way, so that we make sure that we have repeatable results and that can put up to scrutiny. So I think with that, thank you for the attention. And I think we have some minutes for Q&A.
Thank you very much, Eric. Yeah, we do have at least 2 minutes, or it's 3 minutes for Q&A. Any question, please put this on the chat and we can pick up the question. I forgot to mention one thing. Obviously, my first EAGE session, local chapter session, is that this session is obviously recorded because we want to promote and others to also learn. So just for all of your awareness, and as we mentioned before, if you have any question, please do put on the chat box. I don't see any questions so far. We can give, but I can ask a question, a very short question, Eric, just to warm up things here. Fantastic, Eric, as usual, integration, nothing is a silver bullet here to solve, which is going to solve your problem. You gave very good example on collaboration with TGS and Earth Science Analytics. One question is, do you have any, you as a company work together on OSDU specifically, where you saw the benefit of collaboration as such, anything around that?
Yeah, I think that is very fundamental that we achieve this. So we deploy our software, the well-based part of it, with this release number 2, and demonstrated that in the OSDU forum. And we're working on also going for the release 3. So fingers crossed for fast progress and solid progress on that. I think this will be a game changer when individuals and companies developing innovative applications can utilize such a system. So it will really spawn more innovation and collaboration.
Thanks, Eric. I guess with this, we can move on to Steve Freeman, please. If you can share your screen. If you still have a question for Eric, we will hopefully we'll have some time in the end to go through questions. Over to you, Steve.
Very good. Let me just share. Very good. And Surendra, if you could let me know if you can see the screen okay?
Yeah.
Very good. Fantastic. Well, now, thanks very much for the opportunity to present, and congratulations to all the the people that put the work into to create the Stavanger chapter. Kind of long overdue, probably, given the importance of the region in the energy industry. So great, and congratulations for making that happen. What I'm going to talk about for the next kind of 20-25 minutes is partly what was just discussed about there, but more focused on the lower carbon parts of that system, and how we actually make our existing kind of higher carbon systems kind of lower carbon, and fundamentally kind of why we need to do this and what is the pace that we need to work at. Now, given this is an EAGE audience, I'm going to kind of obviously kind of highlight the role and the relevance of geoscience in a number of these particular aspects as we go through. Very good. Okay, so to start with, then, fundamentally the driving forces behind this change, and I think it's impossible to turn on any sort of media or pick up any type of media and not see what's going on around the world with energy transition. If you want to dive into the science of it, then there is absolutely an enormous amount out there, and well encapsulated by the 6th assessment report from the IPCC, just before kind of COP26. Coming out with a very strong agreed statement from all of the governments and the scientific community to say it's now undeniable that human-led influence has created changes on every continent and every ocean around the world. Right? So that's the clear kind of view, and the entire all industrialized nations, all nations are trying to be able to rapidly decarbonize for the benefit of all of our futures. Now, clearly, energy has a huge amount to play in that space, and what we're showing in the center there is kind of one view of many of what the evolution of energy consumption is looking like across the world. Right. So our current position is the kind of the dotted blue line in the middle, in through there, just after the dip associated with the pandemic that we're currently going through. Looks back, 4 decades, looks forwards, 2-3 decades, right? And what you can see is the main chunks of energy in through there. So coal is the blue piece down at the bottom. Oil is that piece that you can see that's grown very substantially over the last 20-30 years. And then you've got natural gas over the top. You can see a little slither of yellow coming through there, which is hydrogen. And then you've got that very big growth segment, which is electricity, sitting on the top. Okay, so that seems to be the general view of where the world is moving towards. And what you can clearly see is that oil demand increases slightly from where we are today, but then is likely to soften as we go forwards. It looks like natural gas is going to be reasonably strong going forwards. There's going to be a dramatic increase in hydrogen production and consumption, and the biggest mover is electricity. Okay, so we are going to see the most rapid transformation of the energy industry that has happened in living memory. Okay. When we talk about what the role in the geoscience community is, really we need to be able to deliver this lower cost, lower carbon energy across all of these pieces, and there is a role for the geoscience community in just about every single one of those particular pieces, and we'll look at that. So when you're in the energy transition space, one of the most common phrases people use is that there is no silver bullet. Right? There are many different things that have to happen, and they have to happen in concert. Right? So if we want to achieve kind of net zero, then we're really looking at how do we allow for increased energy production at the same time as seeing dramatically greater electrification, substantial reduction in emissions from oil and gas operations, the rapid growth in renewables, dramatic scale up in hydrogen, and then scaling up in CCS to be able to abate the hardest to abate sections. So all of those pieces have to happen, and many of those pieces have a key input from geoscience. From Schlumberger's perspective, so I'm the head of energy transition for the digital and integration parts of Schlumberger, which includes things like carbon capture and storage, all the digital pieces around kind of hydrogen, offshore wind, and so forth. What I'm just showing here is some kind of context of the view that we're taking here, that we're kind of sharing. These are the energy transition projects that we've historically done around the world. So it's over 200 different projects in all geographies around the world. And then the colors in through here represent the type of projects that relates to. So the dark blue in there are the carbon capture and storage projects that we've done. The light blue is the low carbon energy generation projects, and that kind of greeny type color are emission reduction projects. So I guess the key takeaway is that activity in every part of the world, the relative type of activity varies from different location to location, depending on the nature of the resources and societal demand and so forth. What I'm also showing over on the right-hand side is our commitment inside Schlumberger towards net zero. So we were the first major energy services company to come out with a net zero commitment for scopes 1, 2, and 3 in through there. So anyway, with that kind of backdrop, then we'll look at a variety of different challenges that face the world and how we can all help to contribute to drive the energy transition. So, for us, it really is about rapidly scaling solutions in each of these core areas. So, the 3 core areas that we routinely come back to around oil and gas emissions reductions. So natural gas and oil will be produced and consumed for a long time to come. We need to ensure that happens with the lowest possible emissions. Not just for oil and gas, but for every other heavy industry on the planet, we need to be able to have a way to be able to mitigate those emissions. And carbon capture and storage is clearly one of the key levers that can be pulled. And it's not just people like ourselves who deploy that at scale. It's people like the IPCC and so forth who are very much kind of clear on that. And then the third one over on the right-hand side is around low carbon technologies. So whether we're talking about things like hydrogen or offshore wind and solar. And again, there's a key input from subsurface and geoscience in all of these particular pieces, but it may mean that we need to change kind of our view of what we do and how we do it to be relevant or most relevant in this future space. So first of all, look at kind of the oil and gas side, and I've made the gas word bigger intentionally, and that's because we're going to see generally a move away from oil and a general increase and a focus more on natural gas. And we can ask the question, what's required for oil and particularly natural gas to be relevant as we go forwards? And so on the left-hand side, we've kind of got the challenge from a kind of exploration, development, production point of view. And on the right-hand side, we've got the challenge about, what happens about the carbonization content of it. So on the left-hand side then, what we need to be able to do for particularly things like natural gas is to be able to identify lower CO2 sources of natural gas that can be produced at low energy and with low emissions. Okay, so there's certainly a requirement for better kind of exploration and targeting of those kind of resources. And we've seen over the last few months across the world the impact of not being able to produce enough low carbon natural gas for the world. Then the next piece is very much, it has to be low cost operations. You have to deliver this lower carbon fuel at a low cost. And then critically for both oil, but particularly gas, is we need to be incredibly clear about delivering low emission systems. Okay, and that low emission system is what I'll just talk about in a second on the right hand side. So what we want to have are fuels that allow us to decarbonize our operations. So natural gas does have 2 opportunities for us. One is around it being a transition fuel, right? And so here you're talking about taking a higher carbon fuel and starting to use a lower carbon fuel. So in this case, it would be if people are currently burning coal, then switching to a natural gas system, can potentially halve the CO2 coming from those kind of systems. Right? And the second opportunity is around creating blue hydrogen. So being able to take natural gas, steam reform it, and be able to have a decarbonized fuel that can be used. Now, they only work if the fuel that is generated is genuinely of a lower carbon content, right? And that's what we need to be incredibly clear about, right? So if you can demonstrate for its entire life cycle it has a lower carbon footprint, then we're moving in the right direction. And what you see on the graph on the bottom there is if you take all of the world's gas producers, how much methane do they leak while they produce that gas? Okay, and you've got the percentage emissions along the bottom. So great news for Stavanger and Norway. You have the world's cleanest, lowest emissions natural gas, right? Almost down at 0%. But you can see there's a very wide range in through there to places which have in excess of 5% leakage. The colors on there represent how good that natural gas would be at decarbonization if you compared it with, say, coal, for instance. Okay, so if you were on the right-hand side in those red areas, that fuel can actually be more carbonizing than if you were using coal. Whereas if you're right over on the left-hand side, those green colors, natural gas then is actually delivering about half the carbon footprint compared to coal. So it's super critical that we're not just looking at natural gas, we're looking at low carbon natural gas, and it's produced in a way that has very low emissions if we want to succeed on the energy transition. Okay, so if we look at oil and gas, then typically we want to be able to drive out emissions from every part of the stack. We want to achieve net zero really by 2030, particularly in Europe. So we need to eliminate methane emissions, just talked about. We need to eliminate flaring. We need to be able to scale up automation and electrification, many of the things that's just been talked about around the digitalization of all of these pieces. On the subsurface side, we need to be able to explore and find the right nature of these assets that need to be producible. We need to have a tight linkage between subsurface and surface operations to ensure that the lowest energy is used to be able to produce those. And then at the surface, we need to have very careful view on what the emissions are that are coming from those and lower the entire footprint of the operation. And clearly that needs to be verifiable and transparent as well. Okay, so that's kind of on the oil and gas side. Carbon capture has relevance in oil and gas, but more it has relevance to every other industry in the world. So we're currently working on over 30 CCS projects worldwide. The majority of those are not for oil and gas operators. Okay, so very much how do you decarbonize all of the world's heavy industries? To give you a sense of scale, last year the world sequestered about 40 million tons of CO2. To align with, say, the IEA net zero 2050 target, the world needs to sequester about 200 times that amount every year to 2050. So a 200 times increase in capacity for the world is required. That's for geological storage of kind of fossil fuel derived CO2, but clearly there's an interesting need to be able to take non-fossil fuel CO2 and decarbonize and sequester that. So looking at bioenergy, carbon capture and storage, and direct air capture, both of which we're working on. So there you're looking at potentially having negative emissions technologies. So one of the ones in through there that we have is a project that we're working on where we're producing electricity, but we're sequestering the CO2 from that biofuel system, and that's delivering negative emissions energy systems. Okay, and if we look at the kind of things from a geoscience perspective we need to do, this is an example from one of our operations in North America. You've got, what is the nature of the seismic acquisition and the wireline acquisition that needs to happen? How do you forward model what will happen when you inject that CO2? And then when you put that asset onto operation, how do you have the right monitoring systems, the right risk evaluation systems to continuously monitor and optimize that system? An example of kind of where CCS needs to get to, particularly with a subsurface kind of focus over on the left-hand side, very much kind of tuning the technologies that we've got, in this case, kind of machine learning for wireline interpretation, tune that to be able to best respond to CO2 related systems. In the center, it's around kind of combining multiple different types of data sets together to get insights. In this particular case, my colleagues used wireline data and seismic to use machine learning to automate the imaging of CO2 in the subsurface. But interestingly, in the low carbon space, what's required is ever more amounts of integration and digitalization. So over on the right hand side, it's very much around being able to digitalize the entire system from the emission site through the transportation system through into the subsurface system, and have that almost towards an autonomous situation. So that's carbon capture and storage. We jump on to low carbon energy systems. Then what I wanted to do here is give you a sense of how much the world needs to increase its capacity. We've done that with CCS. Now we'll look at renewables. So geothermal, the world needs to increase its capacity by about 3 times between now and 2030. Okay, so Schlumberger is involved in about 80% of the world's geothermal projects worldwide. And we're seeing that kind of ramp up in projects happening in through there. Offshore wind is an enormous growth area. So what we're looking at here is a 10 times increase in capacity between now and 2030. And anybody Europe-based or anywhere near the North Sea will clearly see that activity is happening, but it's also now spreading very rapidly into places like Korea, China, Australia, and the US. If we look at the role of geoscience, on the left-hand side of these rapid ramp-ups in capacity that's required, on a geoscience perspective, then what we've been doing is looking at how do you enable faster characterization of the subsurface so that you can design and then build these wind farms more rapidly. So using very high resolution seismic data and wireline data and machine learning workflows to be able to accelerate that characterization workflow. And this is an example of some of this work that we've published with Ørsted, who are the world's largest offshore wind developers. Here using machine learning to be able to interpret the seismic, using machine learning to integrate that with geotechnical data to be able to get these insights about the strength of the sediments to be able to de-risk these offshore wind operations. If we switch from offshore wind to geothermal, again, massive ramp up in requirement to meet the world's need in through there. So there's about a 3x increase, and this year was the first year we saw more than 200 wells being drilled for power generation geothermal, and that needs to just kind of keep ramping up as we go through the rest of the decade. So I think we'll all be fairly aware of geothermal for power generation, which is some of the slides we're showing at the top. What I'm showing at the bottom, though, is an interesting area that's growing quite quickly, which is around using shallow geothermal for heating and cooling systems. This is being able to extract heat from those buildings and store it in the subsurface in periods of high temperature, and then be able to swap that in periods of cold temperature. We created a company, Celsius, to be able to do that, and this is actually one of them deploying one of those operations on one of our sites, this one out in Paris. And so you're able to create this kind of borehole array that allows you to manage the heat on these kind of commercial buildings, and in this case this lowered the carbon footprint of that building by 90% by putting it on that system. And the last one I'm going to touch on is around hydrogen, clean hydrogen. So this is kind of both blue and green hydrogen. You can see the kind of numbers in through there. There needs to be a massive increase in capacity to be able to meet the demand to decarbonize the hard to decarbonize industries of the world. These are particularly the chemicals industry, the steel industry, the heavy transportation industries, and the long duration energy storage industries. So we're working both on the blue and the green hydrogen sides and through there. But we're seeing this all around the world, a huge shift towards hydrogen, which is a fantastic move. So just a brief view of kind of where we see the world changing rapidly. Massive focus on reducing emissions from oil and gas operations, a huge increase in carbon capture and storage capacity, and then really a phenomenal increase in low carbon energy generations. Now, interestingly, as a geoscientist, it's great that there's a whole bunch of geoscience that's involved in many of these particular pieces. So the world is going through the largest transformation in the energy industry that we'll have seen in our lifetimes. Low carbon energy is absolutely the future and will power our future world. The world needs us to be able to deploy these technologies as rapidly as possible. Geoscience will have kind of key inputs into many of those particular pieces. And if we kind of get behind this, then we're really helping address the world's biggest challenges. So with that, I will stop sharing.
Thank you, Steve. Again, thanks for your great presentation. I guess Victor had a question and Eric already replied. If we have any question for Steve, please do write in the chat box, please. We have around 9 minutes for all of us to ask questions to Steve. I'm looking at the chat box if we get a new question. While people are typing, Steve, again, thanks for a great presentation. I don't know how much you can quantify, but if you can talk about a bit about the pace with which this energy transition is happening. And if I may add to that question is, what are the key challenges, one or two of your favorites, which you think can actually double the fold or 50 times fold the pace of this energy transition? If you can talk about these 3 points.
Yeah. Oh, go on. Do you want to run them again? Please surrender. I was getting confused there. So key challenges. Okay. So I think one of the biggest key challenges is making sure, and this is very much to kind of Eric's point, is that this all needs to make money, right? If it makes money, then businesses will get behind it and it will happen. So, a lot of the technologies like offshore wind, now no longer need financial support from governments to work, and therefore those projects are being built purely on a commercial merchant type basis. That makes a lot of sense. There are a number of the technologies, particularly things like carbon capture and storage, and very much kind of hydrogen, where the economics is currently not there in that kind of value chain, and that's where you need kind of governmental support to do that. And congratulations to people like the EU, people like Norway, people like the UK government, who've all put forwards considerable kind of monies to be able to jumpstart those particular pieces. Right? And if we can ensure that the money is there for people to innovate and to scale up, then I think we all have a pretty bright future in this space.
Any other question for Steve?
Okay, interesting. Okay, so the question just come in. So what is your vision on nuclear energy and hydropower? Okay, so thanks, Francisco. So nuclear energy, it's rather bimodal. So if you go to the nuclear power, positive countries, so here you're particularly talking about places like France and the US. And more recently the UK, then they see nuclear power as an important part of the puzzle to be able to cover baseload power. So essentially, how are you going to replace your combined cycle gas turbines or your coal-fired power stations? They're seeing nuclear as the mechanism to do that. Now, one of the challenges with things like nuclear is their ability to be able to scale up and scale down. And therefore, you need to work out how you can potentially store energy. And so people are looking at, do you start to couple energy storage devices with things like nuclear devices so you can have more flexibility? Hydropower, interesting, particularly for Norway. I mean, you are potentially Europe's battery. You have incredible resources there with zero emissions. So existing hydropower makes a huge amount of sense. It is by far the lowest cost source of energy storage, and has by the largest volume by a chunk. There are environmental challenges with it, so therefore the production of new hydropower systems is really quite challenging in many spaces. So hopefully that that answers those particular ones. There are some interesting pieces about looking at kind of high density hydropower under the ground. But,
So you can see 2 more questions there.
Yep, sure. So from Daniel, what role do you see collaboration playing within the energy transition? Now, a great question. So there is no one company, there is no one organization that can do this stuff fast enough. The world needs the energy transition to happen faster than it's ever done any transition before. And that needs all companies, all players and society to work together at a level that it was never comfortable doing before. So yeah, we are absolutely seeing a dramatic acceleration in these kind of partnerships and collaborations, and it's a very healthy thing, and we all need to very much support that. And then a question from my colleague on the presentation here, so from Eric, how to handle fluctuations in wind and solar. So it is a very interesting question, and it kind of partly relates to the 1-2 up. So things like energy storage is critical. Clearly, kind of hydropower or kind of pumped hydro is the biggest, most successful kind of storage device to date. We are seeing lithium-ion batteries provide very good capabilities, say for 2 to 3 hour storage. So they're very good at kind of balancing kind of on a daily basis from grids for places like things like California, where you've got pretty regular intermittencies. But when you're looking at long-term intermittencies, which you see, say, in Northern Europe, then you need to be able to harvest that energy and store it for potentially months. And that's where things like hydrogen, green hydrogen come in. And then for the geoscientists, it's then how do you store that vast amount of hydrogen, and clearly putting it under the ground is quite a good way that we've been able to prove out many times in the past. So again, there's a geoscience component that very much comes into that ability to manage those intermittent energy systems. But the world is solving this challenge, and a lot of it is solving it with digital. There's very much around how do you digitally optimize all of these pieces.
I guess thank you. With this, we move on to Egil for your presentation and questions, answering the questions. Thank you. Over to you, Egil, please.
Thank you very much, Surander. I will share but I'm not allowed to share, it seems like. So I think I need some assistance here now. So I see a blank screen when I try to share. So sorry about that.
Can you see the start sharing button?
Yeah, but it's blanked when I try to share it.
That should offer you an option between sharing your entire screen or
I can do that, but that is also grayed out. There it is. Weird. Okay, hang on. I think I can make it. All right. Good. I got it. Wow, that is good. So thank you very much for being invited to this great seminar. Yeah, my name is Egil Tjaland. I'm an associate professor at NTNU, and I will share some ideas about the history of our education from NTNU within the geosciences, and also about the future and the transition that we are focusing on today. So here is the university that I belong to. It's a university with a long history. So I will give you some statistics just in the beginning here now. So it was founded in 1910, then for mining technology and geology, and then it continued into the oil and gas in 73, where we had the startup of Department for Petroleum Engineering and Petroleum Geosciences. And then we also went into an international study program in 93, which is a master program, international master program for petroleum engineering and also petroleum geosciences. So all in all, I think we have examined or graduated more than 2,500 graduates from our programs within both the petroleum engineering and also from the geosciences. So it's quite interesting to listen to the transition talk of the previous talk here, because when we founded the university in 1910, the main industry was that for mining. And actually, we have been doing a transition ever since. So what we see now is another kind of rotation of that wheel, where we will go to other courses, other disciplines for having attractive opportunities for new students. So I will talk about that later on. I will also say something about our studies at NTNU, and that has been the great and close collaboration with industry. The whole idea of setting up NTNU, which was then called a technical, I shouldn't say high school, but it was actually a Hochschule based on the German system in 1910. And the idea was to have university kind of studies serving the industry. So we have kept that ever since, but we have also developed into a full-size university, and NTNU is the biggest university in Norway with 40,000 students plus. So I just give you some ideas about the industrial cooperation. Here's a very nice picture from one of our field courses that we did on Svalbard. It's a geoscience field course. It was run in the period from 2001 to 2014, and it was funded by Equinor. And we had, I think, 1,400 students on that course. And it was a course for all, not just geoscientists, but also for petroleum engineers, drillers, reservoir engineers, production engineers, and so on. And it was a great experience. And we would not have been able to give such a very kind of good course if we hadn't had this close collaboration with the industry. In this case, Equinor. Here's another example. This is actually a picture from our Schlumberger lab at NTNU. We made a framework a cooperation agreement with Schlumberger in 2014. And this is one of the products from that. We have a special room. And as you can see, it's based on visualization. We have pieces and so on. And actually, we run Petrel courses there. I think we have one of the biggest Petrel fleets in the academic world, more than 50 licenses. And I can also say that when we talk about skills from our universities within the geosciences and petroleum engineering, we also, one of my classmates actually was one of the founders of the company that made Petrel. So it kind of, we have always been kind of working towards digitalization, and I'm not the youngest here, I guess, so there are some years since this was made. I give another example from industrial cooperation, and that is a very nice setup. I will come back to that a little bit later, but it has to do with motivating our students, because at the end of the day, we need the young talents. Bioenergy, they actually started a program where they give 75,000 kroner to 2 students making the best studies at our petroleum engineering and geoscience master courses. So here you see the bright and happy winners. From left, you have from 2020, yes, and from 2021, and to the right, the 2 from 2020. So it's a very good motivation for our students to work hard. We actually look at their grades and give them the prize from there. When it comes to the need to change our study portfolio, we have, in addition to the basic courses that our students will do in the first years of their study, then we have looked into new areas that have been mentioned today. We have courses in CCS, CO2 sequestration, both on geophysical monitoring, 4D seismics, and also for mapping of potential sites for CO2 injection, which is, of course, becoming a very important area, where we will use the seismic interpretation courses, for instance, that we have for interpretation for oil and gas, but we can use the same software and the same skills for finding new sites for CO2 injections. Then we have another area which I don't think we have mentioned too much today, but that is the plugging and abandonment of wells. On the Norwegian shelf, we have some 8,000 wells that need to be plugged and abandoned in a safe way. Now, and you know, that is for eternity. It should not leak. And how do we monitor that? Well, a good candidate is 4D seismic for that. So this is an area where we train our students or through research projects and also in courses. Then we just heard from the previous speaker about geothermal energy. That is also a place where we can use our kind of conventional skills from seismic interpretation, but also from reservoir engineering and production engineering knowledge, because we need to find out what is the depletion rate of the geothermal plants, and also, of course, finding the right places to do that work. And now another thing which I think is important here, and that brings me a little bit back to the first slide I had, where you had the founding of NTNU in 1910. Then the main focus was mining. Now we know that deep sea mining, marine minerals, is a very hot topic. And actually in Norway these days, we have an impact assessment running by the Norwegian Petroleum Directorate on the feasibility and the on deep sea mining in the North Sea. And this is an exciting theme, which is also popular amongst our students, but we can also use existing courses to train students to use geophysical methods like, well, not just seismic methods, but also electrical methods and magnetics, gravity, and more, in order to map these potential rich deposits. Of course, seismic is also an important element here. So if we look at what is really needed by our students to be attractive, I think first of all we need to tell our students that it's important to work on to new ways of looking at energy. We have heard all the new types of energy. We need to train our students to be ready for a job where we also have other energy than oil and gas. That brings us into the new focus areas, of course, where we have ammonia, CO2, hydrogen, and so on. And then I also would like to say a few words about the skill development that our students need to do a good job, and that is actually teamwork. So when it comes to the training, the most important thing in my mind is that we need to keep the solid basis of our training for our students. That means solid foundation in maths, physics, chemistry that we already do. And of course, solid knowledge of geology and geophysics. So we need to keep the base. We even though we are looking into new areas of energy and new ways of doing teaching, we need to keep the basic training there. Then we add and change the course material to the current curriculum as is possible. Sometimes it's a little bit hard to do that amongst all the other courses, but we have the possibility at NTNU to do that during their master thesis and project thesis before that. So that is normally what we have been doing in the past, and that is what we will do also now. Then we need to help our students to be attractive for the work market. And that, of course, means we need to help them with digital competence. And one example is that Python is now compulsory for all exercises in our courses. We give courses in machine learning, and digitalization is a key word, and it's a key topic that we also hear from our students. Some of the students do, as they did before, take courses from other more digital study directions to kind of be more prepared to solve the problems that they assume is needed in their work career. And then, as I said before, we need to include the skills with the new emerging areas. And the list is, as I mentioned, geothermal energy, CCS, hydrogen, ammonia, wind, and so on, and all these things that have been mentioned before. So let me say a few words about the teamwork, because that is something which is quite unique for NTNU. It started up in 2000, I think, around 2000, and it has now been run for about 20 years. And it's a multidisciplinary teamwork where we actually have a certain topic, and all students in their fourth year will need to select a certain theme that they will use one semester to work on. That means 1 day a week for 14 weeks. And the interesting thing with this course is that it focuses on interpersonal skills and teamwork related to project work. And actually, we give a 50% score for the personal skills report, and 50% for the project work. And at our department, we've been running this all from the beginning. And I myself have been running the VR, the virtual reality village, since 2003. We also have had Gullfax and Haltenbanken village. And this has actually been funded by the framework agreement with Equinor. So when we started this, we actually had this as kind of role examples for the other. I think there are now 100 courses in this expert team with 100 different topics, and now every course have been asked to find an external sponsor or kind of a supporter, like we did in the beginning. So that also emphasizes the need, I think, to have a close collaboration with industry. It helps us to do good courses with relevant problems, and it also motivates the students, and it's good for the companies that they will also meet students. So here it is, one of my wishes to you from the industry, and that is, I mean, one thing I didn't mention, but which is important, is that it is hard to attract students to oil and gas these days. I guess you follow the newspapers that the student recruitment is dropping. It has been dropping ever since the fall of the oil price in 2014. And now it's kind of at our university, it has a kind of steady 20 students per year within the oil and gas disciplines. So I think in order to motivate young talents, I mean, this is the biggest industry we have in Norway. So it's so important to get good talents. And one thing I would like a challenge to you sitting in the companies, that would be to actually invite students for a short stay. So let them see the company, and then you can show them this exciting industry. You don't need to hire them, but you could give them a short stay to kind of encourage them and motivate them. And you can also motivate the students, as you have for as long as I can think of, come to NTNU and visit the students. Just a small visit. We had a visit by Schlumberger this autumn, and it was highly popular. I mean, we filled a room, 50, 60 people there coming in to listen to Schlumberger in that case. What is the chance for getting a job, and what is the problem you're working on, and so on and so forth. I showed you the prices that Bioenergy is giving now. I mean, that is also very motivating for the students. And then, I mean, I showed you the Svalbard course in the first slide of our cooperation with industry. I mean, we have also had funding of other courses from other companies, both to Spain, to France, to UK, US, and so on. But it's so important to get kind of experience with field courses for our students. So I would encourage you to think of sharing some of your great field courses with our students. They deserve that. So as I say here in the last statement here, I mean, industry, you have a very important role to encourage students to start a career in geosciences. If you say that there is a job for them, if you say that this is exciting, you have exciting problems to work on, exciting jobs to work on, then you motivate young talents that we need. So let me finish this with some final words. We have provided the industry, and not just in industry, but Norway and Europe and the world, with top experts within the geosciences for as long as NTNU has existed. And we have an ambition to continue to provide industry with core competence within the geosciences for traditional and transitional energy for the future. So, thank you.
Thank you, Egil. We have one generic question on the chat box. I don't know if you can read, if I can read out. I mean, this is for all the panel, all presenters here, especially around where do we see the synergy about the three presenters, what they presented today. And obviously we could see some of it's already through your presentations, but if you want to say something about it.
So surrender, was that to any of
Yeah.
the yeah.
Yeah.
Okay. I mean, I think there's a kind of consistent theme coming through, right? I mean, there's you know, we want to make sure that all of our people are, you know, relevant in this future world, whether it's kind of how do we train the people from the university stage, you know, how do we kind of ensure there's kind of engagement in the current energy world and then into the future energy world, and there's a theme of digitalization that comes through that, whether that's kind of providing them the capabilities to be able to do dangerous things in Python, whether it's going through to giving them kind of machine learning jujitsu skills, or, you know, through every single kind of piece. So I think that kind of staying current and building for the future and pivoting to make sure we're relevant in the future is a pretty consistent theme, I think, from my side.
Yeah, comment from me. It's important, I think, to show all the kind of technologies that you have shown us today to our students. So that was why I encouraged you to invite students, actually. You could do that, of course, with digital webinars like we do now, but still, it's so important, I think, to motivate students, because they will motivate their friends and, you know, cousins and so on, people that will then go into this industry. I'm afraid, to be honest, I have to be a bit serious here now, that within the next 10 years, there will not be many graduated geoscientists in Norway, at least, because there are so few students entering the universities, not just NTNU, but all universities, at least in Norway.
Yeah, maybe I can comment also. For the students, I wish when I was a student I had spent more time than learning to code. I did some courses, but I think today definitely focus on that. And the times are changing dramatically, so just find a way to love to learn new things and adopt to the changes. I think if you build up a good kind of education and knowledge pool in digital, you'll be very adaptable to move wherever the world takes us. So you can be working in geoscience, and you can have the freedom to jump to other fields with this digital knowledge. But there's definitely exciting problems we're working on in the digital geoscience, so I would highly recommend that. It's super interesting. And this encouragement to like to learn and embrace learning, it's not only for the students, it's also for people of all ages.
Thanks, Eric, Steve, and Egil. Any other question we have? Please write on the chat box. We still have 6 minutes. I guess you all presented so well that there's no question anymore. I'm just looking if anyone is typing. Sorry, apologies. No, I think
they're overwhelmed with the excitement of a new chapter in Stavanger. That's the challenge, Surrender.
That's the way to go, indeed. Yeah. No, but I think I can just quickly summarize. I didn't plan for this, but really sincere thanks to, of course, Ilyara for arranging this, and Eric and Steve and Egil for accepting and presenting here. I find it very informative, and I'm sure many others. And hopefully, when posted, it will enlighten many others. With this, if anyone has any presenter or anyone has any comment, please say it. Otherwise, we say bye-bye to all of you and look forward for another session where we will see all of you or more. Yeah, a very good point from Victor. Quick, of course, anyone who is in the participant audience, please do give it your feedback. What kind of next sessions you would like to have? We will be happy to receive emails from you so that we can work towards something which you are more interested in. But overall exciting, and thanks a lot again to all the presenters here. With this, over and out, and hope to see you all somewhere sometime soon, online or physical. Bye.
Brilliant. Thanks, everybody. Have a great day.
Thank you.